Good morning and welcome to the workbench. Today we're going to be talking about relays, and unfortunately we're going to have to spend a lot of time talking about the relay and very little time talking about the Raspberry Pi Pico. But you really can't use the relay, without going into great detail with the other, the Pico. On my bench here, I've got a little sampling of what we're going to be looking at. A few modules here. You've probably seen these on Amazon and some of the electronic sites and so forth. This one here, you certainly have never seen before. This is one I built, I'm going to guess 25 years ago, give or take, probably about 20 years ago. And this was the old acid etch process before I switched over to isolation milling and all that. As you can see, it's rather primitive and all that, but it functioned very well in the device that I had. And that was just a large relay board to handle a lot of I/O and protect a microcontroller that I was using at the time. Oddly enough, this was designed for 5 volts, and it works remarkably good at 3.3 volts. In fact, from what I'm seeing, it actually worked better and more reliable than most of the offerings I'm finding out there in module form. The important thing to remember or understand about relays, their purpose is to allow us, with our microcontroller, to control a very powerful device. It could be a DC controlled device or it could be an AC controlled device. In the DC world, it could be 12, 24, 48, 100 volts, up to around 10 amps or so, maybe even more depending on the size of the relay. For the AC world, in the size that you'd typically be controlling with a Raspberry Pi Pico would be 200 volts in Europe, or here in the US, 110 or 120 volts. And then the amperage rating would be relative to whatever the load is that you're trying to control with it. And we'll go into some of that here shortly. Now, as mentioned, we're going to be talking about using relays with a Pico. And what I want to cover in this video, and hopefully it won't take a really long time to cover all this, but what I would like to do is get this information covered. To understand what we need, first we have to understand the Pico's capability, what its output is to control other devices. And that's very minimal. This is a 3.3 volt device. It can drive approximately 10 milliamps, and that varies with how many different devices you're controlling with the Pico. Supply voltage, supply current, a lot of other things will influence that. But I found that if I stay at about 10 milliamps or 0.01 amps, things behave pretty well with the Pico. The total package shouldn't exceed about 100 milliamps across all the different outputs. So even though you got 10 milliamps per output with 20 some outputs, you would be in that 200 milliamp range. You're going to violate the rules of what the Pico is capable of. Now, we might get into understanding sourcing and syncing for controlling relays. And in that case, sometimes you get a little better output current capability. If we source the power to the relay to switch it on, we have to provide all the voltage and current. If we're syncing that voltage and current into the output, then you get a little more leeway because typically microcontroller outputs can sink more current than they can source. That gets into a lot of discussion, so I'm not sure how far we'll dive into that. Now, relay specifications, that gets into a discussion, and that'll immediately follow what we're going to do here as I'm doing this overview. But it's important that the very first thing you look at for any relay that you're going to use for some purpose is to understand what it is capable of in forms of switching and load. Your switching volts, and amps for DC are often different than using the same relay for switching volts and amps for AC current. I won't be going into any of the AC stuff other than just pointing out specifications. I'm a firm believer that if you are new to electronics, that you should seek hands-on help when working with mains voltage, and that's anything AC voltage at any level other than the most lowest of levels, which is very rare that we would play with it in our world. But what we're looking at here is these are the two most important things. Understand that we want a relay that can handle what it is we want to control. Then we'll need to know the coil voltage, which is how we turn it on and off with its coil. And then finally, the coil amperage or resistance, so that we can understand how much force, how much current it's going to take to turn that relay on or off. Now, a couple more little things I want to point out before we go into the deeper dive. We must supply enough voltage and current to actuate the relay. We can give it 3.3 volts, but that doesn't mean we're giving it enough current to drive that magnetic coil to close the contacts. And that's a very key aspect of what we'll discover here, and that you have to understand as you're working with using relays. And then never use a relay with a contact rating, that would be these two items here, that is less than needed, meaning that you should always overspec a relay, never underspec it, and certainly try to favor in the positive overspecking range as much as you can afford. As mentioned, I want to take a look at the specs of the actual relay, regardless of whether it's a small reed relay like this guy, or a cube like this one, or these two, or on a module. The most important thing is the specs that are on the actual relay, because we are trying to control something of a higher level of power than what our Pico is, and we need to make sure this device can handle that. And luckily, almost all relays have enough information on their cover plate for us to ascertain if it'll work or not. Now, this particular unit, over here on the left, it's saying it's rated for 10 amps at 250 volts AC and 10 amps at 30 volts DC. This particular unit here is rated at 10 amps at 250 AC, 10 amps at 30 volts DC, and then other ones will have similar ratings or additional ratings where it would be where you're switching at full load, full current, or whether it's sustained current going through the relay, etc. You will want to reference the data sheets as well. We'll be taking a look at a few examples of those here shortly. Now, on the relay cover plate will be another very important thing to know. And on these module styles, it's slightly less important than if you're working directly with the relay itself. And that'll make sense here in a minute. Now, on this one on the left, this module, as I recall when I bought it many years ago, was rated at 5 volts. And if I look at the relay itself, here's the manufacturer name and then their part number. In the middle, it gives a DC 5 volts. And that's pretty much assured that is the coil current on this relay. And there's no other circuitry over here to amplify that or give me a different option of it. So I'm pretty confident it was built for 5 volt control. Over here on this one, here's your manufacturer name again. Down below is the model name and number. And here's a 0.3 volts DC. And that, again, would be your coil current. Now, understanding the coil current, it almost is best for us to look at a drawing, a schematic drawing of the inside of a relay. Here's the inside of a relay. It's a very nice schematic of it, perhaps even hand-drawn. It's very old. I see it the way it's kind of been scanned and so forth. But what we want to do is look at two sides of this. Over here, from this area and to the right, all this area is what is being controlled. In this case, they're showing an electric motor and then a high voltage power supply. And again, that could be DC or AC depending on the rating for the relay itself. And this is what they commonly refer to as the working circuit. Up here is the armature that works with the electromagnet. Now, when this electromagnet is energized, it pulls the armature down, closing the contacts here and here, and you will get sparking in there, or commonly referred to as arcing, depending on the voltage and current. But once these contacts make, that completes this circuit and the high-powered device can operate. Now we have to make sure we're pulling this down with enough force. If we don't, we could have further arcing and degradation of these contact points. If we put too much power into here, we could magnetize this and it may not release over time from the capability of the spring. So in other words, this becomes so magnetized, it's held down and the spring can't open it again. And there's oftentimes on data sheets, they'll even say minimum or maximum voltage for guaranteed release of these contacts. Now you'll have a spring, as I mentioned, to open up the contacts. The coil is the device that closes the contacts. And this down here would be our control circuit. So we would have our low voltage coming in. For example, this over here to the left might be the Pico's output pin. Here is the output pin connecting it. So now we're putting in 3.3 volts, energizing this coil. And then the return current path would be the other end of the coil going back into the Pico on the ground side or 0 volt side. So we have to provide enough energy in here to actually close the contact quickly and to hold it shut. Otherwise, you could get arcing and degradation of your contacts, which is a problem that older relays suffered from substantially, and people used to actually have to open up the relay, file the contacts, clean them up a little bit, and then get the thing back running again. Now, before I leave this, I just want to touch on what happens with this coil. This coil, an electromagnet, as is anything where we're magnetizing something and energizing it, electric motors, coils such as this, electromagnets, etc., they build up or have what's called an inductance in them. And when we energize it or de-energize it, there can be a large high voltage spike coming back out of this device, and that could feed back into your circuitry of your Pico. Now we're putting in 3.3 volts, but when this thing releases, it could generate much higher voltage and push that into your Pico, frying it. So we'll take a look at why it's important to address that issue as well. Now let's take a look at a basic circuit with the Pico, some batteries, a motor, and a few other gizmos. Of course, we've got our Pico over here, and in our case, we'll be powering it either through the USB port or through the pins over here. And that would be roughly, we're going to put in 5 volts. Once we're inside this area, of course, any output will be 3.3 volts, which is traditional for the Pico. Now, in this case, I'm showing this as our output. So we're using apparently pin number 24 here. And that would go into the coil side of the relay. And then the return path for the current and electricity would be back on a ground wire going into a ground pin on the Pico. So we want to switch it on, we turn it on, put output, turn that output on, that energizes this coil, and that pulls the armature one way or another to either the normally open contact or to the normally closed contact. Now, on this side, we've got our high-powered motor that's running at 9 volts, and we can see the power coming off of that goes into one side of the relay, and then we would connect our device that we're controlling to either the normally open contact or the normally closed contact. In this case, I guess the way they're showing it, this would be closed, and this one would be normally open. And then with energizing, that would push the armature and connect the circuit, and the device would run. And this is pretty typical of the minimum, absolute bare minimum of controlling a device with a relay. Now, earlier I alluded to the fact that when we turn this relay on or off, there's energy in this coil, and that will reveal itself when we turn it on or off. The traditional way and a minimalistic way of handling that is to put a diode in this area of the circuit. We would literally connect it from here to the wire here, and then from here to here. And what that will do is allow current, when this relay closes or opens, and we get that large spike of energy, it gives that electricity a place to go besides back into the Pico frying its brain. So what'll happen, it'll go through here, up into the diode, back to here, and recirculate. Some of that energy will recirculate back through that coil until it dissipates. And of course, some of it will also go back through the positive wire into the Pico. And that's typically called a flyback diode. And so those would be very typically found on many relays that have control circuitry with them, such as these modules here. Now, I am going to try to find one with a big enough diode that we can see it. Well, because some of the diode, here we go. This diode you can see on a commercial relay module. Right there is the diode, and that's handling that function where we would go through and open or close the contact, and that spike would recirculate through, in this case, the black and red wires, where in this example, the yellow wires are signal. Another device that you may find in the circuit is a transistor. Now, our Pico can only source 10 milliamps, give or take a little bit. And that's not enough to drive most of these coils. So what you have to do is boost it up somehow. And that's where a transistor, basically an amplifier, is used to amplify that current high enough for the circuit to complete. And again, on these modules, I'm going to say that there would be probably a transistor serving that purpose. From what I can see, it's got 3 legs and it's about 3 feet from my face, so I'm just going to guess on that. But you'll see relays or transistors. I think we've got one here. And I'm going to guess right here would be another one. And those, of course, are amplifying that current. And they can be, if you use a transistor, then you might need a resistor with it and a few other devices. So it starts building complexity of the circuit. And that allows us to get control of it. This handles the flyback spike of energy that we don't want. And then the last thing that oftentimes you'll see on circuitry is an optocoupler. And that is an optical isolation device so that from our Pico, our control signals only go through on the internally of an optocoupler. There would be an LED in there that would turn on. So our connection mechanically is only on the light side of the optocoupler. On the opposite side of that would be the control circuitry to continue on from here into the relay. And that too would consist of a transistor, a diode, and several resistors. But as you can start to imagine, this amount of circuitry gets more and more complicated and often requires a circuit board, etc., to utilize them. And that's why modules such as these are so handy for makers. It's got all the stuff built in for us, and we don't have to deal with it, so to speak. We will find out that we actually still have to deal with some of the similar problems, but the safety is built in for us. So we've got more to investigate on this before we can say, yep, go ahead and use that relay module. It'll work perfectly with your Pico. But hopefully this diagram here gets you familiar with the general circuit for using a relay. Not a complete circuit, but gives you the concept of it. To give you an idea of the severity of these voltage spikes, up here on the screen, I've got some screen captures from the scope. I spent a few hours trying to get examples or recordings of the spikes coming off of a relay. Technically, in this case, it was a solenoid, but conceptually, what I'm showing you is the same. Now, sometimes it might be very small like this. Now, what you're seeing here, if you're not familiar with the scope, from this point to this point, going vertical, is 1 volt, according to this. So here we're saying that that spike is maybe 3 volts. And then we've got some random static in there, probably as I'm trying to get the alligator clip to touch the contacts on the signal side of the coil. But that's really nothing to get too excited about other than a lot of nasty noise. Now here it starts getting a little bit more serious, and you see this crazy stuff over here, and unfortunately at 500 nanoseconds or half of a microsecond, it's hard to understand what we're seeing there. This one helps make it much clearer, and you'll see this giant jump here. We get the spike. This is probably the current oscillating. Then we get this giant spike, and then it'll settle back down and then flow out. Now that's 2, 4, 6, 8. It's over 8 volts positive and over 8 volts negative in that spike. So it's pretty tremendous, and it can actually be much higher. As you can see, it's going way off my scope down here. So we do want to be very careful of dealing with that, because that is enough energy to destroy the Pico, making our circuit unreliable. Some people with a lot of money in their pocket will say, it's only $4. That isn't the point. The point is, when we design something, we want it to be reliable. And this creates a very dark and nasty way of destroying that desire, reliability. It'll creep up and get you at various times when you don't want it to. And it's hard to diagnose. Here's another capture with a little cleaner spike on that one, and that's about all I could really get out of it with what I was experimenting with. Now, the first device we're going to take a look at is the ELF read relay. These are smaller relays. They don't handle a lot of current and so forth. But it's rated at, for the coil, it's rated at 5 volts, and then the resistance of the coil is 500 ohms. And if we look at the data sheet, that would be this guy. Oftentimes you can find the part number and just type it into Google and with the word data sheet, and you'll find the data sheets of almost every single electronic component that is manufactured by a reputable manufacturer. I don't want to go into the contact ratings. I think we covered that quite a bit, and it's also covered here in the data sheet. But what I'm looking for, it's up here, coil ratings, because that's part of our discussion right now. We're on the control side of this, and it's this particular model. I've got 5 volts, and the coil resistance is 500 ohms. And its operate voltage is 3.8, and then its release voltage minimum is a 0.5 volt. So it is a 5-volt relay, yet I can get it to work with 3 volts. And we'll dive into that a little bit more later. Now we'll take a look at the Hamlin reed relay. That one is rated at 5 volts, 500 ohms as well. And I believe that would be this particular data sheet. And here they're talking about generically switching up to 200 volts. 200 volts this can switch at 10 watts. So its contact is quite capable. Here's our contact rating. Down here on the data sheet, we can see our coil data again. 5 volts. And I believe that was pretty easy to determine by just looking at the part number. And again, 500 ohms of resistance. It must be able to operate at a minimum of 3.75 volts, and it must release at a 0.5 volt. Maximum coil voltage it can tolerate is 14 volts. Certainly not something we're going to do with our Pico. Now we're going to take a look at this SAN-U, and that one is rated at 5 volts, 70 ohms on the coil. Notice how the resistance is much different on that coil, and according to this data sheet, it should be operating at 70 milliamps. So we will jump over to that. 12 amp switching, blah, blah, blah. Contact capability, always important when we're considering that side of the device. And then in our case, this particular unit is 5 volts nominal voltage, 71.42 milliamps with 70 ohms of resistance. And then they go into more of the dropouts and etc. for the how the coil will hold. But this is how you kind of work through the data that's given to you or that you can find on the device. And the reason why I say that is oftentimes you're going to buy a relay without having enough information because you're getting them off of the discount sites or Amazon, etc. As long as you got a part number, you can find most of the information. So now let's just do a quick walkthrough of these 3 relays because they're all independent relays, no additional circuitry. When I powered them up, I hooked them up to my lab power supply, and I would rotate up the voltage till I could hear the contacts close, or I got an ohm meter where I would see it conducting electricity on the output side. And at 3.3 volts, it operated at 10 milliamps of current. This is a 5 volt, 500 ohm reed relay. And then when I did it at 5 volts, it was also drawing less than 10 milliamps, which makes sense. More voltage, less current situation. That one worked really good. The Hamlin reed relay had similar performance, but it operated slightly less than 10 milliamps according to the readout on my power supply. We come over to the SAN-U Cube, and that will operate at 3.3 volts at 30 milliamps. And that's kind of a red flag there. And then at 5 volts, it would operate at 60 milliamps, which is counterintuitive, so I'm not quite understanding that. But I can say that at 3.3 volts and 30 milliamps, you don't hear the contact closing solidly. It's kind of lazy, so to speak. So you kind of listen for it and you'll hear it too. I've tried recording it and I don't have the equipment to pick up that little clicking sound. But what I'm seeing here is for utilization, these reed relays in all likelihood will work with the Pico. It's working at 3.3 volts and around 10 milliamps. This one supposedly less than 10 milliamps. So Pico could drive that directly. Over here, this is at 30 milliamps. We don't have that on the Pico for driving current. So in all likelihood, this will not operate from an output of the Pico. Now let's take a look at the next 3. And these will be the modules that we would typically buy off of Amazon or SparkFun, Adafruit, Robot Shop, and all the different electronic suppliers. Now, these often come with no data sheet. So the only thing you really have information on, and if you can read surface mount component part numbers, would be to look at the components themselves and then do the research that way. So in our case, we're only looking here at the coil side of the device, and the output ratings we can see right on the actual relay. So you would find that information there. So I'm going by what I found with these devices. Now, the first one we'll look at, and I did not, like I say, I can't get a data sheet on it. There is no part number for the module. Now, this is the single 3-volt module. It was sold, advertised as 3-volt operating, and even the relay shows 3 volts on it. So I'm thinking, yeah, that's perfect for working with the Pico. This particular one is another single volt device, and this was 5 volt rating. As I recall, it's an older module, but I'm quite certain it's a 5 volt device. Something else gave me a clue on that as well. Part number on the relay is showing 5 volts here. This one runs at 3.3 volts. It was drawing slightly less than 80 milliamps, and it wouldn't switch it. When I cranked up the voltage to 5 volts, it was slightly less than 120 milliamps, and then we were good to go. So that's the actuation on that one. This device here is an older module I've had. I bought it within the last decade, I think. It was rated at 5 volts for switching, as are the relays. They're marked 5 volts. And it would run at 3.3 volts at 40 milliamps, and then 5 volts at 60 milliamps to switch it. So going back to our Pico at 10 milliamps of output or driving current, we're not going to be able to use this one, or this one, or this one. None of them have that ability or range for us to drive it at the currents they require for us to actuate it. So between this group of modules and this, the ELF read relay and the Hamlin are the only two we can control directly with some confidence of reliability. Now, what I'd like to point out, this single 3-volt module was advertised on Amazon as designed for the Pico, which I find very fascinating because we need to get 90 milliamps into it. And if we go with the traditional driving it from the output pin, there's no way this will switch. So again, you got to really pay attention to what you're buying. Now, does that mean none of these will work? No, but we can get them to work with additional circuitry. Now we're going to jump over to the code. I'm really not going to go into a lot of explanation on it. It is very simple to run there. But I do have an example circuit set up here with that 3-volt relay, the single module one. So according to them, this should work. Now, as I mentioned, it won't because it's going to require, I believe it was 80 or 90 milliamps to drive it. We've only got 10, so we're 70 or 80 short. But here is the program that I'm using to test these. Just setting up an output for the relay and then the onboard LED so we can track something's actually going on. Set up a while loop to execute 10 times. Turn the relay on, turn the onboard LED on, sleep for 2 seconds, then turn it off, sleep for 2 seconds, and repeat. There's really nothing magical in the code there. Now we'll go ahead and run it. You'll notice that the onboard LED is toggling on and off. Looking at our ohm meter, which is connected to the common and normally open contact of the relay, it's never switching. And nor do I, of course, hear it switching because, again, I don't have 80 milliamps to give it in order for this to switch. And you can play around with the wiring and these jumpers over here, and I was unsuccessful to get it to work reliably with any of the configurations. And then, of course, the other wonderful part of it is there's no detailed instructions from the manufacturer. And I've run similar tests on all these modules doing the same thing. So at this point, we haven't got a relay to actually operate. Well, technically, I can get these two relays, the read relays, to operate, even though they're 5-volt relays. If we go back to here where my actuals were, 3.3 volts at 10 milliamps or at less than 10 milliamps, they operated perfectly fine. So how do you work with these modules? Getting back to that quad module, it was a 5-volt module, and I found out that it would run at 3.3 volts if I could give it 40 milliamps of power. And at 5 volts, it was 60 milliamps. Kind of unusual, but I'm not going to dive into that rabbit hole. So how do I get that to work with the Pico? Like a lot of these modules, my preference is to use an external power supply. The Pico only has so much power going in it, and it can only handle so much power going out of it. So even if we're at 40 milliamps, to trigger the state to activate the relay or deactivate it, we're using up a substantial amount of power that's at the Pico, and that could starve itself and, of course, reset or not provide enough current to do what we want. So what I've got here on the bench, you'll see that I've got a lead here and here. This is coming from my bench power supply, which you should see on one of the cameras here. And it's set at 3.36 volts, kind of toggling around a little bit. I've got my ohm meter hooked up so I can monitor the action of this relay. And I've got the output coming right out of the Pico going into the channel input for the relay. Then the relay board is powered by these two wires, which is getting its power back from the lab supply. I'll try to put together a fritzing diagram for that so it's a little bit more obvious. So now let's go ahead and run this, and what we should see, notice here that the onboard LED is lighting. It's also lighting up over here on the relay board, and you can tell by the ohm meter that it is also toggling back and forth between open and close. So that's powering this 5-volt relay board with a 3.3 volt external power supply, and we're using the 3.3 volt signal from the Raspberry Pi Pico. Now they do share a common ground, and that's to keep things at the same reference voltage. If you didn't have common grounds, things can get a little bit weird and dicey. So now let's see if we can replicate something like this for that 3.3 volt relay board to see if we can get that one to work. Okay, we've got the 3.3 volt board hooked up. Got the software running on the Pico, no changes there. Of course, all we're doing is turning on the output. You can see I've got the VCC and ground going from my external power supply to this board. And then my signal is coming straight out of the Pico into the input on this board. And you'll see that we're pulling 80 milliamps, but that's all coming from this external power supply to activate it. And by the way, what's drawing all that current is most likely that guy right there, which is the optocoupler. So adding in all those protections can create a lot of problems as well. But as you can see, it's working quite nicely. You just got to take these extra steps with an extra power supply. And it doesn't have to be, of course, a lab supply or anything like that. You could run, if you're running off of a battery or something of that nature, you could be just pulling the power off of that device or off the battery before you get over to the Pico. If you've got a project, etc., with a lot of different components and so forth, you may need to add in another one of these guys, which is a very simple adjustable power supply. They're quite handy. So as you can see, with just the massive amount of power the optocoupler and the coil of the relay is taking, we would consume almost all the power available from that Pico, so it simply can't drive it directly. So we need to add in that external power supply. There's a variety of ways you can do it, and it just depends on the type of project that you're doing. Well, I'll bet you didn't expect this journey to last this long to cover simple use of relays. In truth, they can be very simple. Sometimes you buy the right components by the right manufacturer, and you just plug it in, and you don't have to worry about all this extra stuff. From what I'm seeing most of the time, especially the unbranded stuff coming from a distributor who doesn't care what they're really selling, you'll get into a lot of this crazy stuff. But nonetheless, working with relays takes a lot of skill, a lot of research and digging and trial and error to see how the thing behaves, such that you get reliability out of it. Often you can hack your way through it and you'll be perfectly fine, but it does pay to put a little more time and effort into it. I will have another video, it'll be much shorter than this one, where we're talking about powering many relays and how you go about setting that up, and that'll focus again on that ULN 2803 chip to help with that workload. So unfortunately, this thing ran really, really long, but I feel that everything that I covered was important and required. But if you've got comments about the video, please share them in the comments down below. Let me know if you'd like me to do things differently, more detail, less detail, whatever you need to help you along on your way. Thanks again for watching, and I look forward to seeing you in the next video.